Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is chapter 9.6, and 9.6 is the ratio and root tests. Alright, so let's talk about the ratio test first. And the ratio test is, well, let's see. Let the series associated with the sequence a sub n be a series with non-zero terms. Right? The series converges absolutely when the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. Alright? And the next thing, the series diverges when the limit as n goes to infinity of the ratio of a sub n plus 1 over a sub n is greater than 1. And here I'll put in parentheses or infinity, right? So that's when it converges and diverges. But notice here that we said less than 1 and greater than 1. Well, it turns out that the ratio test is inconclusive if that limit is equal to 1. So if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, that ratio, if that limit goes to 1, it's inconclusive. So we need to figure out a different way of doing things. Alright, so let's take a look at some examples. And in general, what we're doing here is seeing if things converge or diverge, right? So let's see. Let's say that we had this series. The series from 0 to infinity of 3 to the n over n factorial. Alright? So here's what we're gonna do. Well, first let's figure out what our sequence is here. Our sequence a sub n would be just clearly 3 to the n over n factorial. And since we need to figure out the ratio with a sub n plus 1, let's figure out what that is. Well, that would be 3 to the n plus 1 over n plus 1 factorial. Alright, so now, what we want to do here is we're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And what does that give us? Well, let's see. We have the limit as n goes to infinity of the absolute value of a sub n plus 1, which was 3 to the n plus 1 over n plus 1 factorial, over a sub n, which was 3 to the n over n factorial. Alright, at that point, well, let's look at this. We've got a fraction divided by a fraction. That means we can multiply it by the reciprocal. And here, these absolute values are not really doing anything because everything inside there is positive. So we can rewrite this now as the limit as n goes to infinity of 3 to the n times 3. How did I get that? Look at this. From the rules of exponents, there's an exponent of 1 there, right? So just add these two. That's how I got there. So 3 to the 1 times 3 over n plus 1 factorial is the same thing as saying n plus 1 times n factorial, right? And we were dividing by this thing over here. So this over here, we're going to multiply by the reciprocal. So that's going to be n factorial over 3 to the n. At that point, we see some things cancel each other out. That n factorial cancels out. That 3 to the n cancels out. So we end up with now the limit as n goes to infinity of 3 over n plus 1. And as n goes to infinity, this goes to 0. So look at that. 0 is less than 1. Good. So because it went to less than 1, what can we say? Yeah, less than 1. converges absolutely. So the series, and so this tells us now that the series from n equals 0 to infinity of 3 to the n over n factorial converges absolutely by the ratio test. All right. Next one, B. Let's say that we have the series from n equals 0 to infinity of n cubed times 3 to the n plus 1 over 5 to the n. Excuse me. We can't start at 0. We have to start at 1. All right. So, and hold on. Why can't we start at 0? Because we said that we had to have a series with non-zero terms. And in this specific one, if I were to start at 0, that is technically the first term would be a 0 term. So technically we wouldn't be able to use it. So I'm starting at 1 to avoid that. All right, so in here, what's our a sub n? Our a sub n is n cubed times 3 to the n plus 1 over 5 to the n. What's our a sub n plus 1? Well, that's going to be n plus 1 cubed times 3 to the n plus 1 plus 1 over 5 to the n plus 1, right? So let's see what we can do here. We need to take, we're doing the limit as n goes to infinity. We're doing the ratio test, right? So a sub n plus 1 over a sub n gives us now the limit as n goes to infinity of a sub n plus 1. So I'm going to write this over here as n plus 1 cubed times 3 to the n plus 2 over 5 to the n plus 1. And we have that over a sub n, which was n cubed times 3 to the n plus 1 over 5 to the n. All right, that's awful. We've got a huge fraction over another huge fraction. So let's change that. So we're gonna say, well, we know that when we divide by a fraction, we can multiply by the reciprocal. So what we're gonna have here is n plus 1 cubed times 3 to the n plus 2 over 5 to the n plus 1 times, we're multiplying by the reciprocal, so 5 to the n over n cubed times 3 to the n plus 1. Cool. Now, let's see what cancels out here. Well, let's write it this way. Instead of doing that as 3 to the n plus 2, like that, I'm going to rewrite that as 3 to the n times 3 to the second. Similarly, that 5 to the n plus 1, 5 to the n times 5 to the first, 3 to the n plus 1, I'm going to write it as 3 to the n times 3. Okay. Now, and again, those are by the rules of exponents, just like in the previous example. This 5 to the n cancels out this 5 to the n. This 3 to the n cancels out this 3 to the n. This 3 cancels out one of these 3's. So what we get now is we have the limit as n goes to infinity. These absolute values are not really doing anything anymore, but we have a 3 over 5. On top we still have an n plus 1 cubed, and on bottom we have an n cubed. All right. So let's see what we can do there. At this point, we can rewrite this as follows. We can say this is the limit as n goes to infinity of 3/5 times n plus 1 over n cubed. Right in here, essentially, I'm saying that if I have a to the b over a to the c, nope, that's not what I meant. Let's do it as this: a to the n over b to the n. This is the same thing as saying a over b to the n, right? That's what I applied here to go to there. At that point, well, let's see. This thing right here, we can rewrite it. So we can say we have the limit as n goes to infinity of 3/5 times 1 plus 1 over n to the third. That 1 over n goes to 0, right, as n goes to infinity. So we really have there just 3/5 times 1. and right, because it's 1 cubed. So 3/5 times 1 is just 3/5. So answer here is just 3/5. So what does that do? What does that do for us? Well, remember we're taking this limit for the ratio test. 3/5 is less than 1. So what we can say now is that by the ratio test, the series we were working with, which was, what was it? N cubed 3 to the n plus 1 over 5 to the n. N cubed times 3 to the n plus 1 over 5 to the n. We're going from 1 to infinity. Converges absolutely. All right. Cool. Let's do another one. So that was B, C. Let's say we had the series from n equals 1 to infinity of n to the n over n factorial. All right. So let's see what we can do here. What's our a sub n? A sub n is just this, n to the n over n factorial. What's b sub n? B sub n in this case, well, I don't mean b sub n. I meant a sub n plus 1. A sub n plus 1 is n plus 1 to the n plus 1 over n plus 1 factorial, right? And now what can we do here? Let's see. We can write this now as the limit, because we're trying to do the ratio test, right? Of the absolute value of a sub n plus 1 over a sub n is the limit as n goes to infinity of the absolute value of this thing, so n plus 1 to the n plus 1 over n plus 1 factorial over a sub n, which was n to the n over n factorial. And at that point, let's see what we can do. We can rewrite this now as the limit as n goes to infinity. We have a fraction divided by another fraction. We can multiply it by the reciprocal. So n plus 1 to the n plus 1 over n plus 1. Well, n plus 1 factorial is the same thing as saying n plus 1 times n factorial. And we're multiplying by the reciprocal now. So the reciprocal here is going to be n factorial over n to the n. Right? And now, what else can we do? Let's see. In here, these factorials cancel each other out, right? Now what? Well, let's actually look at this. Let's look at this little piece right here. That is the same thing as saying n plus 1 to the n times n plus 1, right? So let's keep that in mind. So what we have here now is the limit as n goes to infinity of the absolute value of n plus 1 to the n times n plus 1, and that's everything on top, right? And on bottom we have an n plus 1 times an n to the n. Look at that. Our n plus 1s cancel each other out. And at this point, I'm going to use this trick again. A to the n over b to the n is a over b to the n. I'm going to use that trick again for these two pieces because n plus 1 to the n and n to the n, they're both raised to the same exact exponent. So the limit as n goes to infinity of n plus 1 over n to the n. And in here, how can we rewrite this? We can say this is the limit as n goes to infinity of 1 plus 1 over n to the n. What is that limit? That should look familiar. That is a very special limit. If you have not come up with it yet, well, the answer is E. That limit goes to E. Now, E is approximately 2.71828182845 with a whole bunch of other stuff. The point here is that that is greater than 1. So what we found here is that by the ratio test, the series from n equals 1 to infinity of n to the n over n factorial diverges, right? Because we had that limit is bigger than 1. So there you go. That's an example of a divergent series with the ratio test. All right, next. So that was C. D. Let's say that we have. All right, so here we go. D. The series from n equals 1 to infinity, 0 to infinity of n factorial squared over 3n factorial. Okay, so let's see what we can do here. Our a sub n here is n factorial squared over 3n factorial, right? And let's see what we can do. A sub n plus 1 would be n plus 1 factorial squared over, and here we've got 3 times n plus 1 factorial, right? And now let's see our limit. We're trying to do the ratio test, so that's a sub n plus 1 over a sub n, absolute value. And here we end up with the limit as n goes to infinity of this piece. So we have absolute value of n plus 1 factorial squared over 3 times n plus 1 factorial. All of that over a sub n. N factorial squared over 3n factorial. All right, I'm going to get rid of the absolute values here because everything here is positive, and I got a fraction divided by another fraction, so we know that means multiplied by the reciprocal. So what we have here is n plus 1 factorial squared over 3 times n plus 1 factorial times the reciprocal of the bottom, 3n factorial over n factorial squared. All right, cool. Let's see now. Let's rewrite some of this, right? What do we really have here? In here with this n plus 1 factorial, n plus 1 factorial really means n plus 1 times n factorial, right? And we have this entire thing being squared. So that's the same thing as saying n plus 1 squared times n factorial squared. We're going to keep that in mind as we rewrite this, right? All right, so now we get here the limit as n goes to infinity of n plus 1 times n factorial quantity squared. Well, actually, no, we wanted to go to that last statement there. N plus 1 squared times n factorial squared over, and then multiply by some other stuff, right? Now, in here, in this bottom piece, let's see what this actually does. Let's keep in mind there. So we have here, if I distribute this 3 into here, I have 3n plus 3 factorial, right? And that's the same thing as saying 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n factorial. All right, we're going to keep that in mind when we rewrite it over here. So that's the piece I want to rewrite. So I'm going to have now 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n factorial. And then on the other one, I'm going to leave those as they were, 3n factorial and factorial squared. At that point, you should see some stuff cancels out. 3n factorial, 3n factorial, n factorial squared, n factorial squared. So what do we have here now? Let's see. We end up with the limit as n goes to infinity of n plus 1 squared over 3n plus 3 times 3n plus 2 times 3n plus 1, right? And well, what would this go to? Well, let's see. In the bottom here, I'm not gonna expand it out, but let's see what we have here. If I multiply these first three terms, I end up with a cubic on the bottom. I've got a quadratic on top. Quadratic on top and cubic on bottom. The cubic is growing much faster. So this overall goes to 0. Alright? And since 0 is less than 1, we know that that is absolutely convergent by the ratio test. Alright. So that was D. E. Let's look at the series from n equals 1 to infinity of negative 1 to the n times the square root of n over n plus 1. Alright, and in here, well, since we need to take the absolute value anyways, I'm going to define a sub n to be, well, the square root of n over n plus 1, and a sub n plus 1 is going to be the square root of n plus 1 over n plus 1 plus 1, right? In other words, n plus 2. Alright, so now, our limit as n goes to infinity of the ratio test, a sub n plus 1 over a sub n. What is that? That's going to be the limit as n goes to infinity of, well, I guess these technically these are here. I'll write them in there. I'll write them in here just for the setup. So we have a sub n plus 1, which is negative 1 to the n plus 1, times the square root of n plus 1 over n plus 2, over negative 1 to the n times the square root of n over n plus 1. Cool. So that gives us now the limit as n goes to infinity of, well, the absolute values get rid of this negative 1 stuff, right? That negative 1 to the n and negative 1 to the n plus 1, they're gone. So what we have is the square root of n plus 1 over n plus 2 times, well, in here, instead of dividing by a fraction, I'm going to multiply by the reciprocal, which is n plus 1 times the square root of n, right? At this point, let's see. We can rewrite this. We can rewrite this now as the limit as n goes to infinity of, watch how I'm going to group these. I'm going to put these two together and over the same thing. So n plus 1 over the square root of n, and then the other two over each other. So n plus 1 over n plus 2. The reason I want to do it that way is because now I can rewrite this to be this. Well, rather than writing square roots, I'm just going to put it as n plus 1 over n to the 1/2. And this piece right here, well, I can multiply it by 1 over n over 1 over n. Right? We can always multiply by 1. Multiplying by 1 changes nothing, just like adding 0. Alright, so in here, now we say this becomes the limit as n goes to infinity of, in here, n plus 1 over n, I can rewrite it as 1 plus 1 over n. I have that to the 1/2. Distribute this 1 over n to each piece. So I have 1 plus 1 over n over 1 plus 2 over n. And as n goes to infinity, this piece goes to 0, that piece goes to 0, that piece goes to 0. So we have 1 to the 1/2, so the square root of 1, 1, times 1 over 1. Ooh. We got 1. We did not make any mistake. The ratio here, I mean the limit there of that ratio really is 1. So what do we do? Well, in here, the ratio test is inconclusive. So we must use another test. All right. Well, let's see. What other test can we use? We have -1 to a power. That should remind you of the alternating series. So what we're going to do here is we're going to try to do the alternating series test. All right. So first, let's remind what the alternating series test was. And it said that to converge, we must pass these two conditions. We must have that the limit of a sub n goes to 0, and we must have also that a sub n plus 1 is less than a sub n, right? That is a decreasing sequence. All right, so let's see. So we had our series was -1 to the n times the square root of n over n plus 1, right? And well, let's see what we do. We need to figure out both of these. So let's start with that limit. So if I take the limit as n goes to infinity of a sub n, well, that would be the limit as n goes to infinity of this thing, right? Well, technically, the absolute value there. So when I plug this in here, I end up really with just square root of n over n plus 1. Well, if I multiply this by 1 over n over 1 over n, because it's the highest degree of the denominator, well, what do I get? I get the limit as n goes to infinity of the numerator. So that's the same thing as saying n to the 1/2, right? N to the 1/2 over 1 over n to the 1/2 times 1 over n. That would just be 1 over n to the 1/2. Right, subtract the exponents. 1/2 minus 1 is -1/2, which is a positive exponent on the denominator. On the bottom, distribute the 1 over n, end up with 1 plus 1 over n. At that point, since n is going to infinity, this right here goes to 0, that goes to 0, so we have here 0 over 1 plus 0, which is 0. Okay, so far, the first condition was met. The next condition. So we need to have, so we're looking for a sub n plus 1 to be less than a sub n, right? And what was a sub n plus 1? Well, that was the square root of n plus 1 over n plus 2. And we want to see how that will be less than the square root of n over n plus 1. Well, I'll tell you this one at this point is a difficult one to try to show that. So let's show you how to actually do this one. Consider the following. We were working with n being greater than 1, right? Essentially. Well, technically greater than or equal to 1, right? So what we can say is that for n greater than 1, and this is going to sound kind of silly, for any value of n greater than 1, 1 is less than n. All right. Well, yeah, right? Because if n is greater than 1, then 1 is less than n. Cool. But we can also say that 1 is less than n. So this implies now that 1 is less than n times n plus 1, right? Because if I multiply this, n plus 1 is going to be some positive value. This first one was at least 1. So I have multiplication of two whole numbers that are both at least 1. Yeah, overall that product is going to be bigger than 1. And well, we have this inequality here. We know that if we add something to one side of the inequality, well, we need to add to the other side for it to continue to be true, right? So what I'm going to add here, and this is where this is, well, where did that come from? N cubed plus 3n squared plus 3n. I'm going to add that on both sides. N cubed plus 3n squared plus 3n. And for now, why did I think of doing that? I'll answer that after I'm done with the problem. Because you'll see what happens here. So let's see. On the right hand side, on the left hand side here, this factors out perfectly to be n plus 1 quantity cubed. On the other side, well, in here, this n times n plus 1, that's really n squared plus n. So if I combine like terms here, I have n cubed plus 3n squared plus 1 squared is 4n squared. 3n plus n is 4n. And on the right hand side here, well, that's really saying n times n squared plus 4n plus 4, which is really saying n plus 1, excuse me, n plus 2 squared. And this side over here is really saying, well, that's still the same exact thing, n plus 1 cubed. Right? Now, from there, well, what we can do here is take the square root of both sides. If I take the square root of both sides, so from here to here, is take square roots. So from here to here, we have n plus 1 to the 3/2 is less than the square root of n times n plus 2, right? Because I'm taking the square root of everything here. And at that point, well, this side over here, this is really saying n plus 1 to the 1/2 times n plus 1, right? Because 1 plus 1/2 is 3/2. On this side, we still have just the square root of n times n plus 2. Here's where the magic happens. In here, if I divide this n plus 1 down here and this n plus 2 down there, in other words, kind of like a cross division, what I end up with is n plus 1 to the 1/2 over n plus 2 is less than the square root of n over n plus 1. And that is awesome, because that is what we have over here, right? I mean, instead of the 1/2, I had a square root, but it's the same exact thing. And that is a sub n plus 1 being less than a sub n. Good, we proved it. Now, what does that tell us? Well, this tells us that by alternating series test, the series that we were working with, which was, what was it? Negative 1 to the n from n equals 1 to infinity of the square root of n over n plus 1. This series converges, right? That series converges. But in here, I want to address something that I alluded to before. How did I come up with this stuff to be added there? I didn't work this way. When I first tried this, for example, this problem out, I started with this, and then I started going backwards throughout all the steps to see, well, can I actually get something that would prove it? And that's how you end up with that, right? So this one is a hard one because you kind of have to start with this one, work backwards all the way up this way to show that this actually happens to be true. All right. But the point is, for this example, actually we're not even done. Why are we not done? Because the alternating series, we show that it converges. Recall that with alternating series, we have to check whether they converge absolutely or if they converge conditionally. And the way we did that was we would check what the absolute value version did, right? We're going from 1 to infinity. That's an infinity. All right. So, well, what does this give us? Well, this gives us the summation from n equals 1 to infinity of the square root of n over n plus 1. And what we want to do is we want to see what this does. If it converges, then we know that by the alternating series it converges absolutely. If this diverges, then our original series will converge conditionally. So what I'm going to do here is I'm going to compare with the series of from n equals 1 to infinity of the square root of n over n, which is the same thing as saying 1 over the square root of n. Let's change all those infinity symbols. Those were awful. Alright, there we go. So now, how are we going to do that? So in here, I'm doing the limit comparison. Alright. So that somehow says comparison. Okay, and what was the limit comparison? The limit comparison was we take the limit as n goes to infinity of a sub n over b sub n, right? And if it went to an actual value, right, if that limit existed, then we know that they both behave in the same exact way. So what I'm going to do here is I'm going to say the limit as n goes to infinity of this thing, that's our a sub n, right? The square root of n over n plus 1 over this thing, 1 over the square root of n. So we get limit as n goes to infinity of, well, we're dividing by a fraction. That means multiplied by the reciprocal. So at that point, radical n times radical n is just n, right? So I have n over n plus 1 with that limit as n goes to infinity. And, well, what does that give us? Well, that's going to give us now the limit as n goes to infinity. Well, the way we deal with these is we multiply by 1 over n over 1 over n, right? Because of the denominator there. So at this point, well, what do we get? We get 1 over 1 plus 1 over n. And as n goes to infinity, 1 over n goes to 0. So this goes to 1. So now that we know that this actually goes to 1, then we know that by limit comparison, both series a sub n and b sub n, I'm calling this over here the series of b sub n, and this one right here is the series of a sub n, right? So by limit comparison test, both series behave similarly. And, well, what did b sub n do? So since the series of 1 over n to the 1/2, and that's a 1/2, there we go, as n goes from 1 to infinity, this diverges by p series. Right in here, our p is equal to 1/2. This tells us now that the series that we were looking at, this absolute value, right, that's square root of n over n plus 1, also diverges. So what we can say now overall, well, we got that the absolute value version diverged and the non-absolute value converged. So we can say that the series from n equals 1 to infinity of negative 1 to the n times the square root of n over n plus 1 converges conditionally. All right, cool. So now, that was example E. And that was a few examples of the ratio test, right? Where the first couple of ones we had that it converged, we had one that diverged, and then one that the ratios has failed. So now let's look at something called the root test. The root test says, well, the series of a sub n converges absolutely when the limit as n goes to infinity of the nth root of the absolute value of a sub n is less than 1. All right. Just going to copy that and change it. 2. The series of a sub n diverges. So actually, just cross that out. Diverges when this limit is greater than 1. And, well, the test that reached the root test is inconclusive when the limit equals 1. All right. So those are our three different outcomes for the root test. All right. And notice it's very similar to what the ratio test was, right? When it was less than 1, it converged, absolutely. When it was greater than 1, it diverged. And when it was equal to 1, it was inconclusive. So let's look at some examples here. So example F. Let's say we have a series from n equals 1 to infinity of e to the 3n over n to the n. All right. So let's see. Let's use the root test. The limit as n goes to infinity of this, the nth root of e to the 3n over n to the n, right? And at this point, well, what does that do for us? Well, we get the limit as n goes to infinity. This part inside here, I'm going to write it as e cubed over n, all of that to the n. And then instead of this nth root, I'm going to write it as 1 over n, the exponent of 1 over n. And at that point, well, this n times 1 over n, those right there cancel each other out. So I just have the limit as n goes to infinity of e cubed over n, which is 0, right? Because here n is getting huge, but e to the third is fixed. So at this point, this tells us now, well, 0 is less than 1. So by the root test, our series converges. Absolutely, right? Cool. G. Let's say that we had the series of n plus 1 to the n over 6 to the n, and we're going from 1 to infinity. All right, well, let's apply the root test again. So we have the limit as n goes to infinity. The root test was the nth root of the absolute value of a sub n, right? In this case, that means the limit as n goes to infinity of, I'm going to put it to 1 over n. And what is that we have? Well, in here, notice that they're both being raised to the nth power. So I can rewrite that as n plus 1 over 6 to the nth power. At that point, well, this 1 over n and this n cancel each other out, so I have the limit as n goes to infinity of n plus 1 over 6. And as n goes to infinity, this goes to infinity, right? I probably should have said it over here too. Is greater than 1 or infinity. Well, since this goes to infinity, then we know here that the series that we're working with here, n plus 1 to the n over 6 to the n, diverges by the root test. H. Let's say that we had the summation from n is 1 to infinity of n over 2n plus 1 to the n. All right, and in here, what are we going to do? We're going to apply the root test. So we have the limit as n goes to infinity of the nth root of the absolute value of a sub n. And what does that mean? That means the limit as n goes to infinity of something to the 1 over n. And that something is this thing, right? N over 2n plus 1 to the n. At this point, these two cancel each other out. So we have the limit as n goes to infinity of n over 2n plus 1. If I multiply this by 1 over n over 1 over n, right, I'm multiplying by 1 here. What this gives me now is the limit as n goes to infinity of 1 over 2 plus 1 over n. And this piece now goes to 0. So overall, that equals 1/2. 1/2 is less than 1. So what this tells us now is that by the root test, our series is absolutely convergent. I. So let's say that we had the series from I equals 1 to n. What? That's not what I meant to write. From n equals 1 to infinity, there we go, of e to the negative 3n. Well, let's see. If I do the root test here, so let's say we have the limit as n goes to infinity of the nth root of the absolute value of a sub n, which would be the limit as n goes to infinity of something to the 1 over n, and that something is e to the negative 3, and multiplying those exponents, I end up with the limit as n goes to infinity of e to the negative 3, right? And that's just 1 over e cubed. But 1 over e cubed is less than 1. So that tells us convergent. Technically, absolutely convergent. Now, I do want to mention something about this example. We didn't have to do it with the root test, right? We could have done it with the following. So this is e to the negative 3 to the n. This is the same thing as saying the summation from n equals 1 to infinity of 1 over e cubed, and then all of that to the n. In here, this is a geometric series, right? So this is geometric. And our common ratio there would be 1 over e cubed, right? So in here, that is less than 1 and it's bigger than 0. So by geometric series, it converges. So we didn't have to do the root test on that one. All right, I just wanted you to see an alternative there. All right, so that was I. J. Let's say that we had the series from 1 to infinity of n factorial to the n over n to the n squared. All right, so let's see what we can do here. The very first thing I'm going to do here is I'm going to manipulate this. Let's rewrite it. So we have the summation from n equals 1 to infinity of n factorial to the n. Fine. But at the bottom here, I'm going to switch the places of this n and that 2, right? Because in there, we know that we're going to have to multiply them anyway, and we can rewrite them in whichever order we want. So I'm going to say this is really equal to n squared to the n, right? And at that point, well, what do we do? Well, this becomes now the series from n equals 1 to infinity of n factorial over n squared to the n. And now what we want to do here is we want to do the root test. So the nth root of the absolute value of our a sub n. So in this case, we have the limit as n goes to infinity of the nth root of n factorial over n squared to the n. The nth root and to the n, they cancel each other out. So I have the limit as n goes to infinity of n factorial over n squared. In here, we have a quadratic. Up here, we have a factorial. Recall that factorials grow way faster than quadratics, right? In general, factorials grow even faster than exponentials, and exponentials clearly grow faster than quadratics. So in here, we say that this would go to infinity. All right. So now, infinity is bigger than 1, right? So what we say here is that this is divergent by the root test. Next one, so that was J. Okay, let's say we have a series of 2 times the nth root of n plus 1, all of this to the n. Now we're going from 1 to infinity, right? All right, so let's do this. We have the limit as n goes to infinity of the nth root of our absolute value of a sub n. In this case, that means the limit as n goes to infinity of something raised to the 1 over n, and that something is this piece, 2 times the nth root of n plus 1 to the n. And now, what does that do for us? Well, we end up with the limit as n goes to infinity of, I'm going to write this as 2 times n to the 1 over n, right? And then that plus 1. At that point, well, let's see what we do there. Let's consider this limit by itself, all right? So let's do a little side work, because here, if I plug in infinity here, I end up with infinity to the 0. And well, what does that do? So let's consider that limit. And I'm going to say consider, and we're going to look at this piece. The limit, oh, hold on. The limit as x goes to infinity of x to the 1 over x. All right. So what I'm going to do here is we're going to apply a trick here. I'm going to say let y equal to be that. Then ln of y is going to be the limit as x goes to infinity of 1 over x ln of x, right? Because I just took the natural log of this thing. And I mean, ln of x over, 1 over x over ln of x, that's the same thing as saying just ln of x over x, right? And at that point, what I can do here is we can say by L'Hopital's rule, and why do I want to take L'Hopital's rule? Because if x is going to infinity here, the top goes to infinity, the bottom goes to infinity. We don't like that. That's in indeterminate form, so we apply L'Hopital's rule. And we say the limit as x goes to infinity becomes, well, the derivative of the top over the derivative of the bottom. So in other words, it's just 0. At that point, well, that was ln of y. The question was y. What is y? So in here, since we have ln of y is equal to 0, that tells me that y is equal to e, right? And now that I have that, this is me, e to the 0, sorry, e to the 0, and e to the 0 is 1. So now I've got what that goes to. So how's that helpful? Because what we just found out here is, well, hold on, let me copy and paste this real quick down here. So what we just found out was that this piece right here goes to 1. So now what we can say is that this becomes, well, 2 times 1 is 2 plus 1 is 3. And 3 is greater than 1. So by the root test, the series that we were interested in, which was 2 times the nth root of n plus 1 to the n, is divergent. All right, that is the end of 9.6.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.